Still missing a lot of people. There we go, there's a few more. Alright, okay. Well, we'll submit that and see what happens. Oh, there's more. Okay, good, good, excellent. Good morning, everybody. Hello, how are you? I hope you enjoyed your copious amount of days off from class. Although admittedly, it was not days without work. I had a tough call to make. Either I don't upload the regular weekly assignments on the same day and time as I usually do, and thus everything piles onto the one day of the week we have class, or I continue to post them on the same day and the same time even though we don't have classes on that day. And either you have the time, you can say, hey, I can take a few minutes out of my copious amount of free time today and finish that little assignment that's going to be there every week no matter what anyways. Or hope that Mr. Apple is going to be gracious enough this week that he'll let us turn it in late, even though it was posted at the same time normally. And yet that's what I'm feeling, the last one, okay? So if you didn't get it in time, don't worry, I understand, right? Days off, maybe you made plans, made big plans, things were still posted. Don't concern yourself with that, okay? But for the sake of not spamming you with all the emails ever today, they're going to be posted at their normal times, with the same normal due dates, but I'm fairly flexible there, okay? Just let me know. All right, let's see, I need a couple more in. Isabella's here, and let's see, Perla, did I get Perla? I got Perla. Okay. Still don't see Brianna or Michelle? Nope, Michelle is here. Okay, it moved you up to the top of the list instead of, Zoom, you confuse me sometimes. All right, how about we talk about math? Math is definitely less confusing than Zoom. And as Shakuntala reminds us here, everything is math. In fact, today we've got a wonderful glimpse into some great application of the trigonometry that we've been dealing with all chapter and now into our new chapter, okay? So let's talk about that for a bit. 5.2, the sum and difference formulas. Da, 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 da. You thought the other ones was the only thing? No, there's tons of extra additional types of formulas that you can apply to different trigonometric scenarios. We don't have time to hit all of them. We're just going to get the big ones, okay? So there's the main identities. We talked about that last time. Here we've got the sum and difference formulas. Those are the next biggest, most commonly used, okay? And they're at the very least worth recognizing when to use them, because they'll make your expressions easier to work with. They really will. When they're applicable, they are so applicable and so useful. They're not as common as, say, the Pythagorean identities. Until suddenly they are, right? It's unit dependent, it's field specific as to how much you will encounter these. So this is a great thing to have like on a note card, right? If you're, and this was most of my college calc class, I think actually by Calc 3 we actually were allowed a full page. We got one page of notes that we could bring into the test, to use. This is definitely a great thing to have on there, okay? It is not calculus itself, but it is super useful formulas to make doing the calculus easier, because, oh my gosh, I gotta deal with this thing and I've got these two variables, I can't cosine, right? Both of them at the same time if they're both unknown values. But it separates into cosines and sines of the independent, right, the individual angles, and that you can totally deal with one at a time. Okay, so this is really useful for making things easier in one direction or another, right? And the first question that comes to my mind when I look at this is like, why not just add the angles? right? They give it in terms of right? We see there in the formula alpha and beta. It's like, why don't you just add them together? It's got to be 27 degrees plus 35 degrees. Just add them, right? Well, you can't. There's a reason they are still left as alpha and beta as variables, because a lot of the times when these come up, you're dealing with unknowns. You're dealing with, this is, x. That's your variable. Maybe this is known. Maybe it's x plus 35 degrees. And yes, we understand phase shifts of the function, but that doesn't help you when you have to suddenly take the integral and the derivative of these, okay? When you get to calculus and you have to apply processes to this operation of cosine, the phase shift does nothing for you, okay? Even worse, in a strictly scientific context, you might have both of these, alpha and beta, are your unknowns. Okay? And you do have to continue to treat them as variables, but you still want to be able to simplify and work out, okay, what is happening? Because there's more than just cosine of the sum of these two happening. That's only one part of a much bigger, broader process. Okay? And I bring that up, right? Where is this useful? And the biggest thing that comes to mind is this wonderful, though very complicated, thing called Fourier analysis. And I believe he was French. That's why we don't pronounce the last R. Fourier analysis. And just real quick, let me give you a picture of what that looks like. We're literally dealing with it right now. Microphone and speaker, okay? Sound. Everybody took physics last year. You know that sound travels in, starts with a W.
Waves.
What do we model sound with?
Waves.
Waves, right? Sound travels as waves, okay? And so immediately, oh, look, waves. Sine and cosine look like waves, okay? So we will model often sounds as with sine and cosine functions, okay? We can create the graph. And if you've seen, if you've watched a recording of software, right, that's monitoring the sound, right, picking up, say, run Audacity, right, open up Audacity, hit record, say something, and you'll see those little blips, right, forming on the screen of your voice, okay? But they don't look like simple cosine waves. They don't look like the top thing. They look more like the one on the bottom, okay? Look at that red curve as we've added layers to it. This is cosine on top of cosine on top of cosine, or sine on top of sine. Right? Actual speech, actual vocal sounds, right? Complex things that are more than just a single note from the piano are more complicated. They have many, many notes interwoven on top of each other to create a much more complex tone. Even worse, and what this picture is trying to illustrate is the difference between analog sound and digital sound. Right? A computer is binary. It can have on or off. And so its notes go back to very old video game noises, right? Original NES, even PlayStation era. Right? They could turn on various notes, and it would be abrupt. It's suddenly on and then suddenly off. And you have those square waves like they show here in the blue line. Those are not realistic. You can't create that with an instrument. Okay? But we can approximate it. We can break down, okay, how would you model such a function, right? The square step thing is not a function, right? That vertical line just breaks the whole deal. Fourier analysis does two things. One, it lets us build up functions. We can combine, stack cosine on top of cosine on top of cosine and sine on top of sine to create a almost square function like we have here, right? Notice how the red curve is getting closer and closer to being on top of the blue square curve, right? The square function there. And it also lets us go in reverse. Fourier analysis is that secret CSI tool where you can take a recording of like all the conversations in a room and you can isolate the audio, like to listen to one person talking, right? There's this great bit in Batman Under the Red Hood when his cowl automatically records his experiences, and he's going over it. He was chasing this Red Hood guy across, and he said something, but the train goes by just at the same time. He goes, oh, blah, 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 train noise right over top of it. And he uses some Fourier analysis he doesn't. He runs the computer software, the computer calculations use Fourier analysis to isolate the sound and take out the train noise. Okay? This is audio editing, right? Everybody who makes a video ever runs this. They use these tools. They use Fourier analysis, and Fourier analysis depends upon sum and difference formulas. At least that's one aspect of it, right? It's all of these trig formulas that are used to combine and isolate and make certain expressions into other expressions that are easier to compute and deal with. Okay. That's the application part. There's one last thing. If you look at the textbook right before they give you the actual formulas, there's this bit on the instruments. Okay, and you kind of see the same thing here with the more jagged waves given from the violin create a harsher tone, or the oboe has the richer tone because it's more complicated, right? It's more complex. Does the train example relate to the Doppler effect as well? Oh, you do hear the Doppler effect as well as far as the actual train noise. Right, when it changes tone as it passes by you. That's true. You got that there. And you can, again, model the Doppler effect with more layers. A single cosine isn't going to do it. You got to multiply and divide and add them together, multiple functions on top of each other to create that. Yep, excellent point. Okay. So this is one reason, right, why you got to practice this stuff, just to have a feel for it, to understand what's going on beneath the surface. And if you ever get into any kind of sound design, engineering related field, you'll definitely want to understand a little bit of the mathematics. What's going on behind the screen? Don't just memorize, oh, I click this button and then it just sounds better, okay? Because that's not always going to work. You need to know a little bit of what's going in the background so you can deal with new situations as they come up. So here's one. Write as a single trig function and find the exact value of all of this, okay? This looks like a lot. It's like, oh my gosh, they got the cosine and then the sine and then more sines. It's like 4 different things going on, except if you know your sum and difference formulas, if you recognize, hey, wait a minute, I've got 4 things here, cosine, sine, cosine. I wonder if this is one of those special formulas there. And I could just combine it into a single trig function. Wouldn't that be great? Wouldn't that be so much better to deal with? So let's look, right? We pull out our handy-dandy note card, and we take a peek here. Is there any of them that could work here? Well, notice both of the cosine ones have cosine, cosine, sine, sine. Cosine, cosine, sine, sine. Okay? And so if you want to set up a little mnemonic for yourself to memorize these, I remember doing this back in high school, right? Cosine, cosine, sine, sine. And we change the sign, right? Positive becomes negative, negative becomes positive. The sine function, though, is sine, cosine, cosine, sine. Sine, cosine, cosine, sine. Okay? And we keep the sign. Plus stays plus, minus stays minus. Okay? Set up a little mnemonic for yourself to memorize that as far as what goes. Cosine keeps the cos together in front. Sine is the sign on the outside. Coses go in the middle. But of course, the order doesn't matter. You can swap sine, cosine. Multiplication is commutative, but the important thing is we've stuck with alpha then beta, right? So it's sine of the alpha, cosine of the beta. Okay. Let's see what we have here. In our example there, we have, oh, I'm so sorry. This is not going to work as is. That should not have the 7. There we go. But I checked that. We're supposed to have 2 different angles each time. That's what happens when you get hasty with copy paste. So cosine, sine, sine, cosine. So it's looking like it's one of the sine functions, right? sine of something. There. Is it going to be, let's see, this was still plus, so if we're using sine, we're going to keep the plus there. Now we just got to work out which one's alpha, which one's beta, or does it really matter? Right? Shortcuts upon shortcuts. Hey, wait a minute. The order here doesn't make a difference. As long as I have cosine of one and cosine of the other, sine of one, sine of the other, right? Because, again, go back to the equation. Sine of one, and then the sine of the other one. Cosine of beta, and then cosine of alpha, right? Notice they don't repeat. You don't get cosine of alpha on both sides of the subtraction or the addition, right? You get one of each possible combination. So the order here doesn't matter because they're being added, so it's just going to be 7 pi over 12 plus pi over 12, which, of course, we can immediately combine, and that would be 8 pi over 12, which is, and reduce that, 8 divided by 4, no, divided by 4 is 2, 12 divided by 4 is 3, so it's 2 pi over 3. Okay, where is 2 pi over 3? Is that on our unit circle? Right? 7 pi over 12 I don't think was on our unit circle. This one is. So can anyone tell me what's sine of 2 pi over 3? Let's work this out. Let's see. There's the 45. Pi over 6, pi over 3. Another 45. If this is 1 pi over 3, right, because it's 1, 2/6, 3/6, 4/6, 2 pi over 3. We're dealing with right down here. What's the one right down here? Well, it's the same height as this guy, so I know my y value is a half. No, that'd be the sixth. 1, 2, oh, no, I'm sorry. I can't count. I forgot the 90 degree. 1, 2, 3, 6th, 4, 6th is up here. This is the angle we want. There's 2 pi over 3. Totally forgot to count my 90 degree. Okay, which means our sine is not 1/2. It must be the other guy. It must be square root 3 over 2. Questions on how I did that? Okay, take a look at our next example. Find the exact value of tangent of 3 pi over 4 minus pi over 6. Okay, same question as the first time. Why don't we just add, or in this case subtract? Just subtract them, get one angle, find the tangent of that single number. But then you wouldn't have the exact value, right? Think about what you'd have to do with it. Okay, I got to get a common denominator, which would be 4 and 6 would be twelfths. Are twelfths of pi on my unit circle? No. If they're not on the unit circle, you're not going to get an exact value. Yes, you could get a decimal approximation. You could stick it in the calculator. You can always, always, always stick this in the calculator. And please do use that to check. In fact, I really like the way the book brought that up. I've not seen this very often, like how to actually verify these things, is to run both of them. How do I know that this thing is equal to that thing? Well, did you put both of them in your calculator? Try and cosine of 15. Yes, the calculator is not going to tell you square root 2 plus square root 6 over 4. That's ridiculous. But it can give a decimal approximation for both sides of the equation, and if you get the same decimal approximation, then it's correct. Oh. right? Thinking outside the box, right? You're still using the calculator, but the calculator like indirectly checking it. It's lovely. Okay, so that's a great plan. That's our backup, just in case. Okay, we can always check what's the decimal approximation of this, and check the decimal approximation of our answer and see if they're the same. But I want to use these angles as is because they're on my unit circle. I can get exact values. I just need to split this up into not being the tangent of both of them at once. So is there a sum and difference formula for tangent? Spoilers, yes there is. Absolutely, it's around here somewhere. There we go. It's a little bit beefier. It's got some division in it. Okay, all right. Tangent is always going to be a little bit more complicated than just sine and cosine. Just set yourself up for that expectation. For the rest of your math career, especially in calculus, tangent is always going to be a little bit more complicated. Just is. Because again, think back to the definition. We defined a tangent as sine divided by cosine. It's inherently two functions in one. So of course it's twice as complicated. So here we go. We've got a subtraction here. So we're going to keep the sign up top, flip it in the bottom, tangent of first minus the second, divided by 1 plus the product of the tangents. Okay, tangent of first minus second, divided by 1 plus product of the tangents. Got it. Okay, let me see if I can recreate that here. So we want tangent of first minus second divided by 1 plus the product of the tangents. Okay, how about now? Here we really want to whip out our unit circle if we haven't already. So let me pull one up here just for easy reference. Of course, you could build it from scratch, as I am often do. But for the sake of time, let's just pull one up for reference. Okay, so we've got tangent of 3 pi over 4. 3 pi over 4 is right here, second quadrant in red. So that's a tangent of a pi. Oh, wait a minute. It's just this divided by this. It's just 1. Well, not quite, because it's in the second quadrant. It's -1. It's -1. Okay. -1. So let's go tangent of 3 pi over 4. -1, and this, -1. How about tangent of pi over 6? Handed in a unit circle. Where is pi over 6? Quadrant 1. There it is, the lower angle in blue. So, stop zooming back out. Tangent, TOA, opposite over adjacent. Okay, sine over cosine. Take the y value, the 1/2 divided by square root 3 over 2. All right, if you haven't simplified that before, 1/2 divided by square root 3 over 2, division of fractions, 1/2 times 2 over root 3, 2 is reduced. It's 1 over square root of 3. Or if you want to rationalize the denominator, which would be root 3 over 3. Okay, so this is root 3 over 3, root 3 over 3. With us so far? So now let's continue. We've got in the numerator -1 minus square root 3 over 3. All right, we've got a combined fraction. So let's turn -1 into -3 over 3. So now we have -3 minus root 3 all over 3, all divided by 1 minus -1 times root 3 over 3 is negative root 3 over 3. Wow, this is quite the funky business we got going here, isn't it? Okay, we're gonna have to rationalize this. Let's get the 1 into being the same thing. So this is also a fraction. So instead of 1, we have 3 over 3. So this all becomes 3 minus root 3 all over 3. Yes? I think that's right. Now, let's keep going. I need more space. Oops. Move the next example down there. Okay, so negative 3 minus root 3 over 3 times 3 over 3 minus root 3. All right? So this reduces with that. Good. And now we just need to deal with this in our denominator. I told you it was going to get complicated, but nothing so far is that hard, okay? It's just dealing with fractions. Not too bad. So multiply by our denominator here over itself. Which means we now have 3 times this and this times this. No, not 3 minus, we want 3 plus. Do the complex conjugate, right? That way we get 3 times 3 is 9, but we get a positive and a negative. Those will reduce. And then this root 3 times that root 3 will be root 3 squared, which is back to just 3. So it'll be 9 minus 3. Our new denominator is 6. And up top we have negative 3 times positive 3, so negative 9. And we have this same 3 times negative root 3 and negative 3 times, ooh. Oh, because this one is negative, it does not reduce. All right. So we got minus 3 root 3 minus another 3 root 3. And lastly, minus root 3 squared, which is just 3. So many 3's. Okay. One final step here. Combine like terms up top. Negative 9 minus 3 is negative 12 minus 6 root 3 all over 6. Look at that. Both terms are reducible by 6. Okay? This is one term. This is another term. I could think about it this way, factoring out 6 from the numerator. Okay? That leaves negative 2. That leaves just negative root 3, reducing with the 6, and minus 2 minus root 3 is our final answer. Whew. That took a while. Any questions there? We literally used one simple trick of trigonometry and then turned this into a simplify the rational expression operation, back from Algebra 2, okay? No questions? All right, last one. Here we go. Here is this is the real meat and potatoes, okay? This will give you a good, nice scenario of what a Fourier analysicer might find themselves in if they were doing this by hand. Right? We got to find the cosine of some alpha plus beta, but we don't know alpha and beta. All I know is that the tangent of alpha is 3 over 4, and alpha lies in quadrant 3, and sine of beta is 8 over 17, and beta lies in quadrant 2. That's it. That's the extent of my knowledge. I don't know what the actual angles are specifically. I just know the tangent of one and the sine of the other, but I need the cosine of the combination for Fourier analysis purposes, let's say, right? But our scientific instruments, right, the measurements we have up, our microphone, right, that measures the signal coming from the data sample, whatever it is, right, only gives us this reading. It doesn't tell us the angle itself. So we got to improvise. We got to work with what we got. Okay, well, what we got actually is a lot. Okay, when you are told that a angle is in quadrant 3, you set up a quick set of axes, you draw an angle into quadrant 3. Boom. Okay, so your angle is here. That's the full angle. My tangent, okay, take your angle, draw your triangle. Always draw your right triangle. For this angle, right, call that our alpha. Tangent is the opposite over adjacent, right? SOHCAHTOA, right triangle trig, will save your bacon. Because knowing any trig ratio of an angle can let us figure out any other trig ratio of that angle. So tangent is opposite over adjacent. TOA, opposite here is 3, adjacent then is 4, right? Because it told us to give a fraction. It's opposite over adjacent. It's 3 over 4. So call this 3, call that 4. Bada bing, bada boom. Hey, all I need is this other side. Pythagorean theorem to the rescue. A squared plus b squared equals c squared. Or, since this is a special triangle, 3, 4, this must be 5. Okay, it's not on the unit circle, right? Right triangle trig. Which means now I can find the cosine of alpha. It would be ka, adjacent over hypotenuse, so that must be 4 over 5, right? And the sine of alpha must be opposite over hypotenuse, that would be 3 over 5. That's pretty good. That's pretty good. That's a lot more information than we had. Let's do the same thing to beta. I know beta lies in quadrant 2, so let's draw a sketch of an angle in quadrant 2. Okay? Make it a right triangle with the x-axis. Here is my angle. Call it beta. Sine of bagel. Beta, not bagel. Sine, so is opposite over hypotenuse, so the fraction given, opposite 8, hypotenuse 17. Anybody know special triangle with 8 and 17? That sounds familiar. Now we're going to have to do it the hard way. Google search Pythagorean triples. It's 15. I should know that one. I don't. But I recognize, hey, 8, 17, that sounds familiar, right? Just a quick check. Oh, 8, 15, 17. Right? Pythagorean triple to the rescue. Or you can go 17 squared minus 8 squared, okay. And now we can find, we have sine of beta already, so cosine of beta is going to be, ka would be adjacent over the hypotenuse, 17. Do I need tangent of beta? I could find it. We could write that down real quick. Opposite over adjacent. Am I going to use it? What do I need? Of alpha and beta, I'm trying to find the cosine of the sum of the two. I should at least recognize, if I don't remember the whole formula, the formulas for cosine and sine of sum and differences only include more cosines and sines. I will never need the tangent. I used this tangent, sine and sine. So, cosine of alpha plus beta is, check your formula if you don't have it memorized yet. Alpha plus beta, cosine, cosine, sine, sine, change the sign. Okay. Cosine, cosine, sine, sine, change the sign. So cosine of alpha is 4/5 times cosine of beta, 15/17, minus sine alpha, 3/5, times sine beta, we already had that, it's in the original, 8/17. Okay, anybody know least common multiple of 5 and 17? 5 and 17. 5, let's just multiply. 17 times 5, that's a little too big. That's outside my multiplication table. 7 times 5 is 35. 1 times 5 is 5. 3, 85. Okay, so multiply by 17 over 17. Multiply u by 5 over 5. And need a little bit more space. Do the same thing over here. 17 over 17 multiplied by 5 over 5. And now it's just fractions, right? We're just dealing with fractions. 85, thank you for the confirmation, Fernando. All right, so our denominator is going to be, this is some 85ths minus some other 85ths. 4 times 17. Double 17, you get 34. Double 34, you get 68. What am I doing here? I got ahead of myself. We're multiplying first. We don't need to do this. Why didn't anybody stop me? Just multiply the fractions first. Numerator times numerator, denominator times denominator. Gives us 85. Okay. 4 times 15 is 60. 3 times 8 is 24. I'm overcomplicating things, see? All right, 60 minus 24. 60 minus 20 is 40. 40 minus 4 leaves us with 36 out of 85. That's not what I got. What did we do wrong? Should be more. Should turn into a plus. Why? Because one of these should have been negative. Aha. Aha. Quadrants, people, quadrants. They told us quadrant 3 and quadrant 2 for a reason. Those have an effect on things. This is not just any 3, 4, 5. This is a negative 4. Look at where it is. Okay, plot that in the Cartesian plane. Put this there. It has to be negative 4 to land over here. And this has to be negative 3 to land down there. Tangent, the ratio, negative 3 and negative 4, the negatives cancel out. We didn't notice it hiding inside the tangent. Same thing over here. This is positive, but this must be negative to land in quadrant 2. Which means this is a negative 15. This is a negative 4, negative 3. Ah, shoot. Negative signs. Okay, negative 4, negative 15, negative 3. See the difference now? Okay. This one, negative times negative, positive, doesn't change the 60. This, negative 3 minus negative 24, which means it turns into plus 60 plus 24. $84 out of 85 is our correct answer. How can we verify that? Calculator. Plug that in, okay? All right, final call for questions. No? All right, it's a doozy of one, but we've got a doozy of a day, right? We would have had like almost a full week. We only got the one day this week. Tomorrow, office hours, please, please, please stop by. I will be here. With that is the only thing I have to do tomorrow. So if you have questions on tonight's homework, which is, yes, due Friday, despite not having class Friday, please finish it by Friday, get done and over with, so you can move on and read the next section over the weekend. Okay. I guess if you don't have any questions for me, that's going to do it for here. We'll wrap the